What is the purpose of halogenated polymers and additives in the rubber industry? Welcome back to my rubber heart. Today we are exploring a fascinating and highly technical corner of the rubber industry: halogenated polymers and halogen-containing additives. These materials are widely used, especially where flame resistance and durability are critical. But what makes them so special? And why are they so effective at slowing or stopping fire? Don't worry, we are going to break it all down step by step, including the chemistry, in a way that's easy to follow. Let's start at the very beginning. What are halogens? They are a group of chemical elements found in the periodic table, specifically fluorine, chlorine, bromine, iodine, and astatine. Now, not all of them are relevant to our discussion. In the rubber industry, we focus on chlorine, bromine, and occasionally fluorine. These elements are highly reactive and bond easily with other molecules, which makes them incredibly useful for modifying the properties of rubber and thermoplastics. Halogen atoms can be chemically incorporated in the polymer structure, or they can be part of additives mixed into rubber compounds. Let's start with halogenated polymers. One of the most common is polychloroprene, often known by its trade name Neoprene. It contains chlorine directly within its backbone. Chlorosulfonated polyethylene, or CSM, is another example. It contains chlorine along with sulfonic groups, which add even more chemical resistance. Then we have halobutyl rubbers, like chlorobutyl and bromobutyl rubber, which are modified versions of butyl rubber. These polymers contain chlorine or bromine, making them far more impermeable to gases and resistant to aging. Lastly, we have fluorinated rubbers, like FKM. A trade name such as Viton come to mind. These rubbers contain fluorine, which makes them extraordinarily resistant to heat, chemicals, and fire. So, what about halogenated additives? These are chemicals that are not part of the polymer itself, but are added to the rubber formulation to make it flame retardant. Examples can include brominated flame retardants, which are particularly effective, and chlorinated paraffins, which are widely used as secondary flame retardants and processing aids. These additives are often used in polymers like polyethylene, polypropylene, or SBR, polymers that don't have inherent flame resistance. Now, here is where it gets really interesting. What makes halogenated polymers and additives flame retardant? To answer this, we need to take a quick look at the chemistry of combustion. When a material burns, it's undergoing a chemical reaction with oxygen, releasing heat, light, and gases. For this reaction to keep going, you need fuel, which is the material itself, heat, and oxygen. But the most important part of the flame is the radical chain reaction. This reaction involves extremely reactive molecules called free radicals, like hydrogen radicals, hydroxyl radicals, and oxygen radicals. These radicals are what break down the material into flammable gases, which then keep feeding the fire. Here is where the halogen chemistry comes into play. When halogenated polymers or additives are exposed to heat, they decompose and release gases like hydrogen chloride or hydrogen bromide. These gases act as radical scavengers, which mean they react with the free radicals in the flame, neutralizing them. For example, a bromine-containing flame retardant releases hydrogen bromine when it heats up. The hydrogen bromide reacts with the free radicals, interrupting the chain reaction and essentially starving the fire of the energy it needs to keep burning. In addition to neutralizing the free radicals, this process also has a cooling effect. The release of halogen gases is an endothermic reaction, which means it absorbs heat from the fire, lowering the temperature and slowing down the combustion process. This combination of radical interruption and cooling makes halogenated polymers and additives highly effective flame retardants. Now, you might be wondering, why is bromine considered more effective than chlorine? It all comes down to the chemistry. Bromine bonds break down at lower temperatures than chlorine bonds, which means bromine releases hydrogen bromide earlier in the fire. This allows it to disrupt the combustion process more quickly and efficiently. Bromine radicals are also more reactive than chlorine radicals, so they neutralize the flame's free radicals more effectively. To summarize the big picture, halogenated polymers like polychloroprene and chlorosulfonated polyethylene are inherently flame retardant because they contain chlorine or bromine in their structure. When they are heated, they release halogen gases that slow down or stop the fire. For materials that don't have this natural resistance, halogenated additives like brominated flame retardants are added to achieve the same effect. These materials play a critical role in industries where fire safety is non-negotiable. Think about rubber cables and wire coatings where flame retardant properties prevent electrical fires from spreading, or automotive seals and gaskets where heat resistance and fire suppression are essential. Fluorinated rubbers like FKM are used in aerospace applications because of their ability to withstand extreme temperatures and resist combustion altogether. That said, there is an ongoing discussion in the industry about the environmental impact of halogenated materials. During combustion, some halogenated compounds can release toxic byproducts like dioxins and furans, which are harmful to human health and the environment. Regulations like REACH in Europe and RoHS in electronics have placed restrictions on certain halogenated additives, leading to a growing demand for halogen-free flame retardant solutions. Still, the chemistry behind halogenated materials is remarkable, and their ability to slow or stop fire remains unmatched in many applications. Whether you're working with inherently flame retardant polymers like polychloroprene or using brominated additives to enhance safety, understanding the role of halogens gives you a deeper appreciation for the science that keeps our materials and us safe. Thank you for joining me in this deep dive into halogenated polymers and additives. If you enjoyed this episode and learned something new, don't forget to like, share, and subscribe to my Rubber Heart. Let me know in the comments what other topics in rubber science you would like to explore. Until next time, stay curious and stay bouncy.